Hello everyone, myself B. Vijaya, lecturer in chemistry, working in Indira Priyadarshini Government Degree College for Women, Nampally, and we are discussing the chapter called Coordination Compounds. In the coordination compounds, we are discussing, we already discussed about the valency bond theory, and as per valency bond theory, we have discussed how the coordinate covalent bond will be formed between the central metal cation and the ligands, and why this central metal cation is called as the Lewis acid and why the ligands are called as the Lewis bases, we have discussed in detail. And then each and every postulate of valency bond theory was discussed. If you did not watch these videos, please watch them first. And we also discussed the relationship between the coordination number and shape of the molecule. Shape means here the structure or geometry of the molecules according to the coordination number by the valence bond theory approach. And along with the examples also we have discussed for the square planar complexes, tetrahedral complexes, and for the coordination number 6 complexes, that is octahedral complexes, also in detail with the different types of the examples we have discussed. And the drawbacks of the valency bond theory also we have discussed. uh, Next one is crystal field theory. In crystal field theory, we have discussed the postulates of the crystal field theory, and the shapes of the d orbitals and how the d orbitals splitting of the d orbitals in the octahedral complexes and tetrahedral complexes and square planar complexes we have seen. And the next one is the spectrochemical series of the molecules given by the this crystal field theory we have discussed. So those are means stronger field ligands are there and weaker field ligands are there, and what will be the means how this ligand fields affects or influence the crystal field, we have discussed in my previous videos. So if you did not watch them, you please watch them first. Then applications of crystal field theory also we have discussed, and how to calculate a oxidation state of the central metal cation and magnetic property. A calculation of crystal field stabilization energy was also discussed, right? So in the weak field ligand as well as a strong field ligand. And today our concept is, today we are going to discuss about the crystal field stabilization energy calculation. So as per the examples, by taking one or two examples we have discussed with the how to calculate the crystal field stabilization energy in my previous video. Here I'm summarizing all the means along with the electron number, right? So the means this crystal field stabilization energy was completely depends upon the number of electrons present in the d orbitals, and how the d orbitals, how they these electrons present in the d orbitals were influenced by the this ligand field effect. So that is completely explained by the crystal field theory actually. And as per that, so after splitting of the d orbitals, the electrons are uh, having some of the energy, they acquire some energy. Either the negative energy means low energy they might acquire, or high energy also they might acquire. So as per that energies we are discussing this crystal field stabilization energies. Okay, it is completely depending upon the number of electrons. I am not taking the examples now. For this video I'm not taking any examples. If is there any necessary, I will explain along with the example also. Okay, so crystal field stabilization energy, and this crystal field stabilization energy in which calculations only we are going to uh, take here. So in crystal field stabilization energy, these calculations are we have in our syllabus is Calculation of crystal field stabilization energy of an octahedral complexes with strong field ligands. So here octahedral complexes we are taking and strong field ligands we are taking here. So these two words, this octahedral complexes, this one octahedral complexes with strong field ligands. So how in the presence of strong field ligands in an octahedral complexes, how the ligand fields means that this strong field ligands are influences the electrons present in the d orbitals of the central metal cations of an octahedral complexes. So this was explained today. Means today we are going to discuss about these ones. And second one is the calculation of crystal field stabilization energy of an octahedral complexes with weak field ligands, right? Weak field ligands. And then the next one is the calculation of crystal field stabilization energies of tetrahedral complexes. Tetrahedral complexes with strong field ligands and the calculation of crystal field stabilization energies of tetrahedral complexes with weak field ligands. So here the complex, what kind of the complex we are taking and what is the strength of the ligand here. There is a means for octahedral complexes there is a two types of the ligands, strong field ligands and weak field ligands. So for octahedral complexes, in presence of strong field ligand what happens, in presence of weak field ligand what happens, how they will affect the number of electrons. And in tetrahedral complexes also they can form a coordination compounds with the strong field ligands as well as the weak field ligands also. And so these ligands, how they affect the electrons already present in the tetrahedral complexes. So that we are going to study in the CFSE. Okay, crystal field stabilization energies. And in that first one is a calculation of crystal field stabilization energy of an octahedral complexes with strong field ligand. So here we are taking the strong field ligands like the examples are here for strong field ligands. What are the strong field ligands are there? The examples are carbon monoxide is a strong field as we have seen earlier in the spectrochemical series, and the cyanide, right, Cn minus is a strong field, then the NO2 minus nitro, right? So these are said to be a strong field ligands here. An octahedral complex which is having the complexes which are having a coordination number 6. So those complexes are called as octahedral complexes with the strong field ligand. And for this, what is the means formula we need to use? I will tell you. And the first, I am writing here the number of electrons, right? Number of electrons here I am taking. And for the octahedral complexes, how it will be for the octahedral complexes, the d orbital splits, right? The d orbital splits into two types. The lower energy will be the T2G orbitals and higher energy will be the EG orbitals, right? T2G orbitals means three orbitals will be present. Three orbitals will be present. So these are called as the T2G orbitals and EG orbitals. So the first electrons will enter into the means lower energy will be the T2G. And here I am taking the electrons present in T2G orbitals, and then the next higher energy will be EG orbitals. So the electrons present in EG orbitals, right? EG orbitals. And then I am writing here the formula, right? So what is the formula we need to write? Or the same formula is applicable to complete all the electrons, right? So all the octahedral complexes, the same formula will be applied. So I am writing here the CFSE value. Then what is this? Crystal field stabilization energy value. So if the number of electrons are 1, so better I will change the color of the pen so that it will be easy for you people. So if the number of electrons are 1, so this one electron, where it will enter here if one electron is there. So if one electron is there, this electron will enter into the T2G orbital, right? So one electron will be present. So for better understanding, I am writing in this way, EG orbitals. Okay, so EG orbitals, and so one electron will be there. And what is the crystal field stabilization energy? And this is having a minus 0.4, right? So whatever the electron enter here into the T2G orbital, each electron is acquired a minus 0.4 energy, and this EG orbitals gain a plus 0.6 energy, right? So for the crystal field stabilization energy calculation, so what will be the formula? The minus 0.4, right? Minus 0.4 electrons present in the T2G orbitals plus the 0.6 and into the number of electrons present in the EG orbital. So this will be the formula. This will be the formula, and this we need to know here. We have to apply this formula only here. So for minus 0.4, and how many electrons are present in the T2G orbital? Here one electron is present. So minus 0.4 into 1 electron plus 0.6 into 0, right? So minus 0.4 into 1 will be the minus 0.4 only, and this whole thing will be 0. So that is nothing but minus 0.4 value, which the crystal field stabilization energy value will be the minus 0.4, right? Minus 0.4. And if the electrons, number of electrons are 2 electrons are there, so 2 electrons are present. That means here one more electron is there. So what will be the d orbital? Splits into T2G orbitals and EG orbitals, right? EG orbitals, and so there will be 2 electrons. So these 2 electrons, second electron will enter into the this T2G orbitals only. So since it is a T2G orbital is having 1, and now it is having a 2. So 0.4 into 2 will be the minus 0.8, and the EG orbitals does not having any electrons. So here minus 0.8, it will become minus 0.8. And if the number of electrons are um, sorry, if the number of electrons are 3 electrons are there, 3 electrons are there, and where these 3 electrons will enter, because first they will enter into the lower energy level only, right? These 3 electrons will enter into the lower energy level only, and there are the two types of the orbitals are there, T2G orbitals and EG orbitals, right? So here 1 electron, 2 electron, 3 electron will enter, and now 3 unpaired electrons. So in 3 T2G orbital, 3 unpaired electrons are there, and here uh, just let me rub this one. Okay, so 3 electrons are there, 3 electrons are there. So minus 0.4 into 3 will be the, it will be minus 1.2, and plus this will be 0. So the value will be, crystal field stabilization energy will be minus 1.2, right? This will be the crystal field stabilization energy. So this value will be minus 1.2. And now where the fourth electron will enter. So here the question comes, where the fourth electron. So total number of electrons are 4 unpaired electrons are there. Now these 3 orbitals, we can fill the 3 electrons in these 3 orbitals, and where the fourth electron will enter. So now we have to see whether, means what is the field of ligands, means what is the ligand field here. So if it is a strong field ligand, then the pairing will takes place. This is the important one. So pairing is takes place in the lower energy level only. So in lower energy means already 3 electrons are there, as 3 electrons are present, 3 electrons are there, and fourth electron also enter into the T2G orbital only here. So this point we need to remember. So now T2G orbitals and EG orbitals, right? So T2G orbitals and EG orbitals, and the electron, fourth electron is also enter into the T2G orbital. Now this will become 4 now, right? This will become 4 now. So minus 0.4 into 4 will be the minus 0.6, and there are no electrons present in the EG orbital. So the crystal field stabilization energy will be minus 1.6, right? And the next one is the, if 5 electrons are present, then the pairing will take place in the same manner, that is in the T2G orbital only, not in EG orbital. So the electron, fifth electron will be enter into the T2G orbitals only. So now 5 electrons are present in the this T2G orbital. So 5 electrons into minus 0.4, that is a minus 2.0, right? Minus 2.0. So I will show you once. Okay, now the sixth electron. So if it is having a sixth electron, and this sixth electron also, just like a previous electron, which will enter into the EG orbital, sorry, T2G orbital only. So now total all electrons are paired in the T2G orbitals only. So there are no electrons present in the EG orbital. So total 6 electrons into minus 0.4 into 6 electrons, and plus this will be 0, right? So minus 0.4 into 6 is minus 2.4. So the crystal field stabilization energy of this, the complex, octahedral complex, is, which is having a strong field ligand and 6 electrons are there. So that will be minus 2.4. And the next one is the seventh electron. So obviously the seventh electron will enter into the EG orbital only. Why? Because all the electrons are paired in the T2G level. That means in the lower energy level. So the T2G orbitals are having a all paired electrons, total 6 electrons it is having, and the next electron, that means the seventh electron, will enter into the EG orbital. So now here the minus 0.4, that is 6 electrons are there present in the T2G orbital, plus here in the EG orbital now 1 electron is there. So minus 0.4 into 6 will be the minus 2.4, right? Minus 2.4, and plus 0.6 into 1 is a 0.6 only. So minus 2.4 plus 0.6. So how much it will be? It will be minus 1.8, right? So this is the value for the seventh electron, right? Is that not? So minus 1.8. And if the one more electron is present, that means 8 electrons are present in the this particular complexes which are having a octahedral complexes which are having a uh, strong field ligands, then what will be the crystal field stabilization energy? So all electrons are filled in the Eg orbital and in T2g orbital, and in Eg orbital seventh electron will be here and eighth electron will be here. So what will be the next one? Now it will become 2, right? So minus 2.4 and 0.6 into 2 will be 1.2, right? So this will become minus 1.2. Here the crystal field stabilization is energy is minus 1.2. And then the ninth electron, where the ninth electron will enter? So ninth electron again in the higher energy level, that is the Eg orbital only, it will enter. So total 6 electrons are there in the T2g orbital, and here one electron present in the Eg orbital. So one more electron will be added here. So total how many electrons are there now? Total 9 electrons are there. Among them, this value will be same, minus 2.4. Why? Because minus 0.4 into 6 electrons are present in the T2g orbital plus 0.6 into how many electrons are there? 3 electrons are there. So minus 0.4 into 6 will be minus 2.4 plus this 0.6 into 3 will be the plus 1.8. So if we remove this one, the value will be the minus 0.6, right? So minus 0.6. And then if the tenth electron is there, means the orbital is having a all paired electrons in the T2g as well as the Eg orbitals. The zinc complexes normally are having this kind of the electronic configuration. So zinc plus 2 ions. So all the 6 electrons are there in the T2g orbital, and Eg orbital is also having the 4 electrons. So total electrons will be 10. Now what will be the crystal field stabilization energy? So this I am rubbing here. Now this will be total 4 electrons are there and 6 electrons are present in the T2g orbitals. So minus 0.4 into 6 will be the minus 2.4, and plus 0.6 into 4 will be the 2.4 plus 2.4. So minus 2.4 and plus 2.4, that will gives the crystal field stabilization energy will be 0. So what will be the less crystal field stabilization energy for how many electrons? For 10 electrons it will be 0, and for the 6 electrons it will be the maximum crystal field stabilization energy for the octahedral complexes with strong field ligands. Next, the octahedral complexes with an weak field ligands. And already we have discussed what is the octahedral complexes. The complexes are having a coordination number 6, right? Coordination number 6 are called as the octahedral complexes. And weak field ligands such as the water molecule, water molecule, OH minus ions, and the chloride ion, bromide ion, iodide ion, means all the halogens including fluoride ions also. So these ligands are called as the, means considered as a weak field ligand, as the strength of the ligands are very less on the octahedral complexes. So in this case, what we have to remember is, in the presence of weak field ligand, no pairing will be takes place. No pairing will be takes place. So, and in the presence of strong field ligands, the pairing will be takes place in the lower energy level only. But in weak field ligands, no pairing will be takes place in the lower energy level. That means the d orbitals, for 5d orbitals in presence of ligand field effect, they splits into what? The lower energy level will be the T2g orbitals, right? T2g orbitals, and the higher energy will be the Eg orbitals. So the first electrons will be enter into the T2g orbital, and fourth electron, where it will enter, it will enter into the higher energy level only, not it will be paired in the um, it will not be paired in the T2g orbitals. So T2g orbitals, each electron of the T2g orbital present in the T2g orbital will acquire the minus 0.4, and each one of the electron present in the Eg orbitals will get the plus 0.6 delta naught energies, right? So this will be the crystal field splitting takes place in the octahedral complexes. So in the weak field ligand field effect, means in the presence of weak field ligands, after filling of the 3 electrons here, the fourth electron will enter here, so that no pairing will be takes place. Now let us start our this calculation. So number of electrons, number of electrons present in the d orbitals, and the number of electrons present in the T2g orbitals, and number of electrons present in the Eg orbitals, and crystal field stabilization energy, right? So here, if one electron is present in the d orbital, where it will enter? The first d orbital, first one electron of the d orbital, it will enter into the T2g level only. So T2g orbital only. So here one electron will enter. Better I will write this d orbital, so that it will be easy for us to understand betterly. So these are the T2g orbital, and one electron enter here, and there are no electrons present in the Eg orbital. And what will be the crystal field stabilization energy value? How to calculate? By using the same formula, that is minus 0.4 into electrons present in the T2g orbitals plus 0.6 into electrons present in the Eg orbitals. So here minus 0.4 into 1 electron there, and there is no electrons present in the Eg orbital. So 0 into 0.6 will be the 0 only, right? So here minus 0.4 into 1, this will gives the value minus 0.4 only. So minus 0.4. And if the two electrons present, so they also will enter into the lower energy level of T2g, and there are no electrons present in the Ag orbital. So this will become 2, and the value will become 8, right? So minus 0.8. And if the 3 electrons are present, so each one of the T2g orbital will be get one electron in each. So 3 electrons are there. Now here in the T2g orbital, there are the 3 electrons are there, and this value will be minus 1.2, right? So minus 1.2 will be the crystal field stabilization energy value. And where the fourth electron will enter now? So if the orbital d orbital of an octahedral complexes are having a 4 electrons and in their weak field ligand, so this fourth electron where it will enter? So here there is no pairing takes place like in the previous one. So in the presence of strong field ligands, here the pairing will takes place, but these are the weak field ligands, right? Weak field ligands, so there will not be any pairing. So 4 electrons are there, 3 electrons are present in the T2g orbital, and here 1 electron is present in the EG orbital. So by applying this formula, I will rub this one so that it will be clear. So minus 0.4 into 3 electrons present in the T2g orbital and plus 0.6 into 1 electron present, and minus 0.4 into 3 will be minus 1.2, right? So here already we have calculated this value, and plus 0.6 into 1 will be 0.6 only, and minus 1.2 plus 0.6 it will gives the value minus minus 0.6, right? Minus 0.6. So the value will be minus 0.6. And if the fifth electron is present, where it will enter is, so here the T2g orbitals are having a 3 electrons here, and EG orbital is having a 1 electron if the 5 electrons are there in the D orbitals. So here 3 electrons, unpaired electrons, and fourth electron is there, and where the fifth electron? Obviously into the EG orbital. So here the EG orbitals are also having a 2 unpaired electrons. Now you see here 0.4 into 3 electrons present in the T2g orbital, and in the EG orbital there are the 2 electrons now. That means minus 0.4 into 3 will be minus 1.2, and 0.6 into 2 will be plus 1.2. So the value will become 0 now for the 5 electrons. So the crystal field stabilization energy for the 5 electrons, if the octahedral complex containing the 5 electrons uh, in its means in the ligand field effect, that is weaker field ligand effect, so that will be 0 crystal field stabilization energy. So this is an important point. Okay, now let us see the sixth one, and where the sixth electron enter. Now here 3 electrons are over, here 2 electrons, means so that all the 5 orbitals are having a 1 electron in each. So now the question is where the sixth electron will enter. So the sixth electron now enter into, so here I'm pairing this one. This sixth electron will enter into the T2g orbital. So T2g orbital of a complex now are having a 4 electrons, and EG orbital is having 2 electrons, and now you see this minus 0.4 into how many electrons are there now? 4 electrons are there, and plus 0.6 into how many electrons? 2 electrons. Minus 0.4 into 4 will be minus minus 1.6, right? Minus 1.6, plus this will be plus 1.2. So what will be the difference? The difference will be the minus 0.4, and here I am writing the difference. Minus 0.4 is the crystal field stabilization energy for the 6 electrons present in the octahedral complex of an weak field ligands. And where the seventh electron will enter? Obviously in the lower energy level only. Now the pairing will takes place from the sixth electron onwards. So here in the Eg orbital there will be each Eg orbital is having a 1 electron in each only. Now in T2G orbitals, now how many electrons are there? 3 plus 2, 5 electrons are there. So minus 0.4 into 5 electrons plus 0.6 into 2 electrons. So minus 0.4 into 5 will be the minus 2.0 plus 0.6 into 2 will be plus 1.2. So what is the value? It will give minus 0.8. So this will be the value minus 0.8 is the crystal field stabilization energy for the 7 electrons present in an octahedral complex of weaker field ligands. So now if the eighth electron where it will enter, obviously in the T2G orbital only, so that all the electrons are paired in the T2G orbital, and in the Eg orbital there are the 2 electrons are present. So what will be the value, crystal field stabilization energy value? Let us calculate now. Minus 0.4 into 6 electrons are present because all the electrons are paired in the T2G energy, plus 0.6 into 2 electrons will be there. So minus 0.4 into 6 will be the minus 2.4 plus 0.6 into 2 will be the 1.2, and minus 2.4 plus 1.2. So what will be the difference between these two? Minus 1.2. So here minus 1.2 will be the crystal field stabilization energy for the 8 electrons. And if 9 electrons are present in the d orbitals of the complex, so that now ninth electron will enter into the Eg orbital, so that pairing will start in the Eg orbital also. So here this value becomes 3 now, because all the 6 electrons are present in the T2G orbital. So the value will be minus 2.4, and 0.6 into 3 will be plus 1.8, right? Plus 1.8, and minus 2.4 plus 1.8, which will become the value which will gives the uh, minus 0.6, right? Minus 0.6. Okay, so if the 10 electrons are there in this orbitals, d orbitals of the central metal cation, so that the Eg orbitals and T2G orbitals are gets fully paired with each other, the electrons. So total now here 6 electrons are there, and here it will be a 4 electrons, right? 4 electrons will be present. 6 electrons now. So okay, 0.6 into 4. So this, the value of this one will minus 0.4 into 6 will be minus 2.4, and 0.6 into 4 will be plus 2.4. So the value will become 0. So 0 for the octahedral complexes which are having a weaker field ligands. So in the presence of weaker field ligands, these are the crystal field stabilization energy values. And for the crystal field stabilization energy values of the octahedral complexes are 0 for the 5 electrons as well as the 10th electron also. 10 electrons also it will be less, that means 0 and 0. So these are about the crystal field stabilization energy values for the octahedral complexes.